This conference will now be recorded.
Hello everyone. So we will continue quantitative analysis of organic compounds. So three elements are left: sulfur, phosphorus, and oxygen. So after that, this chapter will be complete. And if we have some extra time, we can also discuss some questions which is based on these chapters. So estimation of sulfur, that is also in KDS tube. We will do the experiment. So that is why the method is KDS method. Here a known mass of the substance, that is the organic compound we will take, and we will heat it with sodium peroxide. So this is the oxidizing agent with which we have to heat it. We can also use fuming nitric acid, and everything should be done in the KDS tube. Now, the carbon and hydrogen that is present in the organic compound, these two elements will be oxidized to CO2 and H2O respectively. But we are here measuring quantitatively sulfur. So what will be the fate of sulfur? Sulfur present in the compound, that will be oxidized to H2SO4. That is the fate of sulfur. Now this resulting solution, once the heating is complete, now it will be treated with excess of barium chloride. Because when it is in presence of barium chloride, the sulfuric acid which is present, because this is the sulfur which we have obtained from the sulfur of the organic compound. Now this sulfate ion will be exchanged with the chloride ion. So this is simply displacement reaction. So it will be quantitatively converted into BaSO4. So this is very simple equation. BaCl2, when it is in presence of H2SO4, it will produce BaSO4 and HCl. Now this that is H2SO4, this sulfur is basically the sulfur from the organic compound. Now this sulfur is present in the barium sulfate. Now why we are doing this reaction? Because barium sulfate is insoluble in water aqueous medium. So that is why we will get it in the form of precipitate. And we can easily filter it, and after filtration we have to wash it, dry it, and finally we have to take the weight of this BaSO4. Now in this case, when we will do the calculation, it will be basically how we will start it. We will start it from that number of moles of BaSO4, that is actually equal to number of moles of sulfur, right? Because per mole of BaSO4 you have only one sulfur atom. Now if it is the case, then number of moles of BaSO4, that is actually the mass of BaSO4. Suppose the mass of BaSO4 is m1 gram. So m1 gram, if we divide it by the molar mass of BaSO4, molar mass of BaSO4. So molar mass of BaSO4, that we have to calculate. So molar mass of BaSO4, how we will calculate? For one barium atom, it will be 37 plus 32, which is for sulfur. There is total 4 oxygen, so 4 into 16. So if we do this calculation, we will get the molar mass, which is 233. So here M1, if we divide it by the molar mass of BaSO4, we get M1 divided by 233, which is basically the number of moles of sulfur. Now once we know this, the next steps are simple. Now we can calculate the percentage sulfur present in the molecule. So known mass of the organic substance that we have taken, suppose this known mass is m gram. So in this case, percentage of sulfur, that will be the mass of sulfur divided by this m multiplied by 100. Now what is the mass of sulfur? We know this is the number of moles of sulfur. So if we multiply 32 with this number of moles of sulfur, we will get the mass of sulfur. So in this way, this will be the final equation. If we simplify it, it will be 32 multiplied by M1 divided by 233 multiplied by 100 divided by M. So in this way, we can calculate the percentage of mass if you know the value of M1 and also the value of M. Next, we will solve this problem and that we can do based on this equation. Even if we don't remember the equation, that is also fine. So simply we will follow the logic. In the sulfur estimation, 0.471 gram of an organic compound. So this is the starting amount of the organic compound. And from this we are getting 1.44 gram of barium sulfate. So this is the mass of barium sulfate and this is the mass of organic compound, right? Now we have just calculated the molar mass of barium sulfate. Here 137, it is again given so that you can calculate the molar mass of BaSO4, which we have already done, and we have seen this is 233. So here number of moles of BaSO4, that is equal to 1.44 divided by 233. Now this is also equal to number of moles of sulfur. Both are same. Now if this is the case, then we can say that mass of sulfur is equal to 32 multiplied by 1.44 divided by 233. If it is the case, then percentage of sulfur will be 32 multiplied by 1.44 divided by 233. Now this whole quantity should be divided by 0.471, which is the mass of the organic compound multiplied by 100. So ultimately we can simplify it. So if we do the calculation, if we from this you will get, which is nearly equal to nearest integer 42. So here final answer will be 42. Okay. Next, again Carrier's method, but that is for phosphorus. Again we will take a known mass of organic compound and that will be heated with HNO3. Not just any HNO3, it is fuming HNO3 and that is also in Carrier's tube. Now once we do this, here the carbon and hydrogen, these two elements present in the organic compound, just like the previous method, there also we have seen these two are converted to CO2, H2 respectively. Here also the same thing. But our focus is on phosphorus. What will be the fate of phosphorus? Here phosphorus, which is present in organic compound, it will be oxidized to phosphoric acid. In the previous case, you have seen it is oxidized to H2SO4. Now it will be oxidized to H3PO4. But we have to make it in the precipitate form. In the previous case, we have converted H2SO4 ultimately to BaSO4 so that you can take the PPT, you can filter it out and you can take the weight very easily. So here also we will do some precipitation. How? This is precipitated as ammonium phosphomolybdate by heating with concentrated HNO3 and then adding ammonium molybdate. So this is the reaction. You have H3PO4, which you have obtained after heating with fuming HNO3. Then you are adding to it ammonium molybdate. Ammonium molybdate NH4O2MOO4 in presence of HNO3. So it is once H3PO4 is formed, again you have to heat it with ammonium molybdate HNO3 when it will be converted to ammonium phosphomolybdate. So this is the molecule ammonium phosphomolybdate and these are the byproducts. Now this part we will get in as the precipitation form. So this is basically a yellow colored solid. Now if this is the PPT, we can filter it out. The precipitate of this thus formed, filtered, washed, dried and wet. Now this is one way by which you can do the precipitation, but there is another way by which also you can do the precipitation. So this is number one precipitate which we can do. There is alternative method also. H3PO4 you can also get precipitate in the form of magnesium ammonium phosphate, which is MgNH4PO4. And how? Now how we will get it? You have to add magnesium mixture. which is basically mixture of magnesium chloride, ammonium chloride and ammonia. Now when this magnesium mixture you are heating with H3PO4, H3PO4 in presence of NH4Cl and MgCl2, now it will be converted to MgNH4PO4, right? So this precipitate of, and this HCl that will be consumed by NH3. So this is the precipitate that we have to ultimately filter, wash and make it dry and then ignite it. So once you have dried it, there is some extra step. So this is not the final step. There is some extra step. We will ignite it. That is heat, high temperature heat. So when you are heating it, MgNH4PO4 will be decomposed to Mg2P2O7. And this is called magnesium pyrophosphate, Mg2P2O7, which is formed on ignition, and its weight we will note. Okay. Now we will do the calculation. So as we always do, the PPT, this is number 1 and this is number 2. So in the previous sulfur case, we have calculated the molar mass of BSO4. So in this case, what we will do, we will calculate the molar mass of first this PPT, and for the alternative method, you have to find the molar mass of Mg2P2O7. So in the next slide, we will do the calculation. Now we will consider first method 1, where NH4 PO4 12 MO, that is molybdenum. So suppose this is having mass m1 gram, but we will find its molecular weight. Okay, just have a look. NH4 PO4 12 MoO3. So we will find its molar mass. Now molar mass of this 3 into, for nitrogen it is 14 and for hydrogen it is 4. So it will be multiplied by 3. Then we have phosphorus, for which it is 31. Then we have 4 oxygen. So 4 into 16. Now this whole quantity within second bracket plus 12 multiplied by 96, which is atomic mass of molybdenum, plus 3 multiplied by 16, which is for oxygen. Now after this calculation, you will find it as 1877 gram. Now in this case, number of moles of this compound, I am just writing it as X for simplicity. Number of moles of X, that is also equal to number of moles of P, because per mole you have just one phosphorus, right? So simply divide M1 by 1877. Now once we have done this, final step is easy. Mass of phosphorus is 31 multiplied by the number of moles of P, which is same as number of moles of ammonium phosphomolybdate. So percentage of P will be initial organic compound. Suppose it is M, so it will be like this. So this is for the first precipitate, but if you do the alternative method, now we have to find the mass of suppose it is having, that is a mass we have obtained after ignition and after drying all this, M2, but its molar mass also we have to calculate. Mg2 2 into 24, P2 31 into 2 plus 7 into 16. So everything if you add, you will get 222 gram per mole. So number of moles of Mg2P2O7 in M2 gram, that is equal to M2 divided by 222, but this is also equal to number of moles of, sorry, this is actually not exactly equal to, it is 2 into number of moles of P. That is basically number of moles of phosphorus per mole of Mg2P2O7. It is basically 2 phosphorus atoms. So if M2 divided by 222, that is the mass of Mg2P2O7, obviously now the number of moles, it will be multiplied by 2. Okay. So I can also write it as Mg2P2O7 equivalent to 2P. So it is 1:2. That is the relationship. Okay. Basically, here we should not multiply it with 2. Whatever you will get from M2 divided by 222, you just have to multiply it with 2. Then only you will get number of moles of P. So I am writing it in this way, that number of moles of phosphorus, that is actually 2 into M2 divided by 222. Now finally, we have to calculate its percentage of phosphorus, which is equal to mass of phosphorus. Now mass of phosphorus, with this quantity you have to multiply 31. So 2m2 divided by 222 multiplied by 31. Then this whole quantity should be divided by m, which is the starting amount of organic compound. So finally it will be 2m2 divided by 222. You can 31 and 2, these two you can multiply, so it will be 62 multiplied by m2 by 222, 100 divided by m. So this is the final expression for percentage of mass. Okay. Now the final element left, which is estimation of oxygen. Now for estimation of oxygen, basically 2 ways you can do it. The first one is indirect interference, and mostly it is followed. The percentage of oxygen in an organic compound is usually found by taking the difference between the percentage composition, which you can consider as if it is 100, and the sum of percentage of all other elements. So all other elements, I mean to say carbon, hydrogen, phosphorus, nitrogen, halogen, sulfur, everything we have seen how to quantitatively analyze. Now if you know the percentage of everything, suppose in your compound you have carbon, hydrogen, nitrogen, halogen, oxygen, and you have calculated all the percentage of CHNX. Now you know it. So sum of the percentage of all the other elements, if you subtract from the 100, obviously you can get. So this is basically subtraction we are doing. We are not directly measuring it. It is an indirect way of measuring. But for this, you need to know the percentage of all the other elements, right? So this is the indirect method. Next, there is a direct method, which is known as Lewis method. Known mass of the compound is subject to pyrolysis, which is decomposition by heat, and that will be in a stream of nitrogen gas. Now, when we are doing this, and why it is in presence of nitrogen gas? Because you cannot do it in presence of air. If you do it in presence of air, it will also, that is extra oxygen will be added from the air, but that we do not want. We just want the percentage of oxygen that is originally present in the organic compound, not from air. So that is, it should be done in the stream of nitrogen gas. The mixture of gases that will be produced. So when you are heating the organic compound in a stream of nitrogen gas, you will get other gaseous products as well as some O2, oxygen. So this mixture of gases should so produce, that will be passed over red hot coke, so that all the oxygen is converted to CO. So in this gaseous products, there will also be oxygen. One of these will be oxygen. But when you are passing it over red hot coke, which is nothing but carbon, O2 will be converted to carbon monoxide. Now this carbon monoxide, the next step that we have to do, this mixture is then heated with iodine pentoxide, I2O5. Now the purpose is I2O5, it will oxidize CO2 and itself will be converted to iodine. Right? So here ratio of CO and CO2, if you compare, this is already a balanced equation. If you compare it, you will see 1 mole of CO will produce 1 mole of CO2. Now in the previous equation, if it is equation 1, if it is equation 2, in the previous equation you have seen that for 1 mole of O2, you are basically getting 2 moles of CO. So finally, if I combine all the three, this should be the ratio. So basically I am combining these two equations and the ratio will be for 1 mole of O2, there will be 2 moles of CO, 1 mole of O2 from which you will get 2 moles of CO, and as CO and CO2 both are 1:1, so it will also be 2 CO2. Okay. So number of moles of CO2 that is equal to or equivalent to number of moles of oxygen plus multiplied by half, right? Now if it is so, now the number of moles of CO2, molar mass of CO2 is 44, and suppose the mass of CO2 we have obtained m1 gram. So number of moles of CO2 should be m1 divided by 44. Now if this is the number of moles of CO2 and if you are multiplying it with half, with this, if you are multiplying half, because number of moles of O2 it should be multiplied by half, you are getting m1 divided by 88. Now mass of O2 in this m1 gram of CO2, which is basically we are getting from CO, and CO we are getting from O2. So mass of O2 should be 32 multiplied by number of moles of O2, which is m1 by divided by 88. Finally, percentage of oxygen, 32 multiplied by m1 divided by 88. This whole quantity should be multiplied by 100. Multiplied by 100 and divided by m, which is the original organic compound's mass. So this is the final expression we are getting for the percentage of oxygen. 32 multiplied by m1 divided by 88 multiplied by 1 by m into 100. Now, though we have seen different methods for quantitative analysis of organic compounds, but as a note, we have to know some extra informations. And what are these extra informations? Presently, though we have seen different methods, Carrier's method, Dumas method, Kejel's method, but presently the estimation of elements in an organic compound, it is not done in that way, whatever you have read, because now modern methods are there. So it is basically carried out in micro quantities of the organic compound. So the organic compound that will be required for this analysis, that is very small amount, and we do it in automatic experimental techniques. So all the detailed steps manually we don't have to do. Okay, automatic experimental techniques are there. Now these elements, carbon, hydrogen, nitrogen, halogen, sulfur, that are present in a compound, they are determined by an apparatus, and that is known as CHNS elemental analyzer. It provides a means for rapid determination of all these elements in organic matrices and also other type of materials, but we are interested only in organic compounds. Now in this case, in this instrument, this process capable of handling wide variety of sample types. It may be solid, it may be liquid, it may be something volatile, and also viscous sample. And as we know, organic compounds are very common in pharmaceuticals, polymers, environment, food, energy. So this is very versatile. Its application is not only limited to organic compounds, but it is also having other applications. But as we are talking about only organic compounds, just know this, that CHNS elemental analyzer, that is the modern method we use for estimation of all these elements. Okay, so this chapter is complete, and as we have some time, we'll discuss some questions, and that will be based on these chapters. With respect to the compounds 1, 2, 4, choose the correct statement, or S, that is more than one statement may be correct. Okay, not a single choice answer. So the first molecule is basically it is methane derivative. Suppose I am writing here methane. But if you replace 3 hydrogen with 3 phenyl groups, now it will be PH3CH. Now in this case, all the options, if you read carefully, it is talking about the acidity. Now if it is talking about acidity, that means after removal of H, you will get PH3C minus. So this will be the carbon. Now in this case, the first option is saying that acidity of compound 1 is due to delocalization in the conjugate base. So this is the conjugate base we are getting from PH3CH. In general, if I write any acid HA, after dissociation it is H plus A minus. So here conjugate base is A minus. If A minus is very stable, that means dissociation of HA to H plus and A minus, that will be very high. That means when conjugate base is stable, acidity is high. Now in this case, conjugate base, which is PH3C minus, it is stable because of delocalization. It is saying that acidity of the first compound is because of delocalization in the CB, conjugate base. And that is true. Why? Because here the negative charge which will be produced after removal of this hydrogen, that can undergo resonance with these 3 phenyl rings. So delocalization is possible. But also one important point you have to remember, that due to steric reason, these 3 phenyl rings, their presence in the same plane simultaneously, that is also a little bit difficult. Now for resonance to occur, planarity is very important. Now that planarity simultaneously for all the 3 rings, that will also be not occur very easily. So though there will be delocalization, but still it is not that it is having delocalization in 3 rings. So A minus is very stable. That means HA is very good acid. But actually that is not the case. It is true that delocalization is happening, but HA is not very good acid. But anyway, option A statement is correct. Acidity of compound 1, it is because of delocalization in the CB. Now the CB of compound 4 is aromatic. Look at the compound 4. If you remove this hydrogen, you get negative charge here. Now this is aromatic. Why? First of all, it is fulfilling the primary condition, which is it is cyclic, it is planar, and conjugation throughout the ring is possible. This negative charge can take part in conjugation. And the total number of electrons that are taking part in this pi delocalization, that is also 6. 2 electrons, 2 electrons, 2 electrons. Total 6 electrons, so it is matching with this format, Huckel's rule. So n value is 1, then you are getting 6 pi electron. So it is aromatic obviously, and conjugate base aromatic means it will be very stable. Acidity will also be very high, because when there is aromaticity factor, that is a aromaticity when it is the reason for the stability. Just understand that it will be very stable, and as a result the acid will be very, that is this molecule will be highly acidic. Compound 2, which is simply benzene ring, if you remove this, there will be negative charge directly over any of these carbon. Now it is saying that 2 becomes more acidic when it has a minus NO2 substituent. Now if you have NO2 substituent present anywhere, obviously it will, because of its electron withdrawing capacity, it will stabilize the negative charge. Conjugation is not possible. It will obviously not show minus R effect, but it can show minus I effect. So whenever there will be, that is, if there is NO2 substituent present in the benzene ring and you are removing this hydrogen, obviously it will be more acidic. So this is also true. Now A true, B true, C true. Is D is also true? It is saying that the acidity of compounds follows the order 1, 4, 5, 2, 3. Now 1 cannot be at first position. Even if you are not sure about the other, 1 cannot be at first position. So it is placing 1 at first position, 4 is at a second position, but that is actually not correct. 3 is at last. It is okay because it is simply methane molecule, and if you are removing H, you will get CST minus and there is no stabilizing factor. If you remove hydrogen from here, what you will get? You will get negative charge over sp hybridized carbon, which is stable because of high S character. But methane, there is no stability factor once you remove one hydrogen. But anyway, just placing 1 at first position, it makes the complete, it makes the order wrong, even if you are not sure about the others. So it will not be the correct option. Now look at this pK value, which will help you to understand in which case acidity is high, because we know pK, it has inverse relationship with the acidity. So when pK is very low, which you can find in this case, that means this should be maximum acidic. 4 should be at first position. And after that, the second position is taken by 5, because 20 is 25. The third position is taken by 1. The fourth position is taken by benzene. And the last position is obviously 3. So this is correct. These two part is correct, but other 3 positions are not correct. So D is not correct, but the first 3 options are correct. So that is why this will be, all these 3 statements A, B, C will be the correct options. The total number of stable conformers with non-zero dipole moment, which you can get for the following compound. Now here it is mentioned that is or are, so it may be more than 1. Now here it is given in the Fisher projection. So if I consider it as the front carbon and this is as the rear carbon, and if I draw the sawhorse, first convert it to sawhorse, because that will be helpful for us before proceeding to Newman. So in the front carbon, Br is on the left hand side, this is chlorine, this is methyl, and in this case BrCH3 chlorine. Now if I convert it to Newman, what I will get, that we have to see, right? So I will not change the front carbon, that is after drawing this, you will see I will rotate the substituents. Let me write it as methyl, because I have written methane for the front carbon. Now in this case, it is asking total number of stable conformers. So it has to be stable as well as non-zero dipole moment. Now first of all, this projection, as directly we have converted this projection, suppose this is number 1, it is not stable. It is unstable, because all the bonds, they are overlapping with each other. It is not staggered, right? So that is why it will not be stable and we will not consider it. Next, if you rotate it 60 degree and the rotation is for the back carbon, rear carbon, then what will happen? Now as I have not disturbed the front, just draw it as it is, but bromine will be now here, methyl will be here, and chlorine will be here. Now in this case, it is comparatively stabler, right? And here also dipole moment will not be 0. So dipole moment here, it is not equal to 0. Because see, bromine, they are on the same side, methyl groups, they are on the same side. So there is no cancellation possible. This part, these two position atoms, if you consider they are opposite to each other, it is okay. But overall, 0 dipole moment is not possible. Next, further if you rotate 60 degree, what you will get? Again, there will be overlapping. So see, front I have not changed. Cl is here, Br is here, Me is here. Now this structure, which is number 3, that we will not consider. Why? Because this is not stable. It is not staggered, right? Next, if I again move 60 degree in this way, now bromine will be here, chlorine will be here, methyl will be here. Now in this case it is staggered, but it is again non-zero dipole moment. That you can understand. Br and Br opposite, but Cl, Cl same side, methyl, methyl same side. So this can be considered as correct answer. We will have to count it. Further, if I remove, if I rotate 60 degree, keeping the front carbon constant. Now chlorine is here. Now this is again something unstable, so we cannot consider it. And finally, further rotation 60 degree. This is number 5. This is number 6. Now, here we will choose this one because it has to be stable conformer as well as non-zero dipole moment. Now, this is stable. This is also stable with non-zero dipole moment. This is also stable with non-zero dipole moment, right? So, these three, this should be considered as answer. But the other three, just let me use different color. The other three, that is the green ones, they are not staggered, so that is why they will not be stable. So only the blue three you have to consider. So answer will be 3. Total number of cyclic isomers possible for a hydrocarbon with molecular formula C4H6. It is already mentioned that it is cyclic. But if you just as there is total number of carbon 4, you can simply start with cyclobutane. But if you do not put any double bond, you will see total number of hydrogen will be total 4 CH2. So total hydrogen will be 8. So you have to put a double bond, then only you will see it will match with C4H6. Now 2 hydrogen, 2 hydrogen, 2 hydrogen. That means total 6 hydrogen. So this type of structure is possible with 4 member. Now if I make it 3 member, now in this case there should be some substituent. Now mere placing some substituent, total number of carbon will be 4. But if you count hydrogen, 3, 1, 2, 2, it is more than 6. So again you have to place a double bond. Then it will be C4H6. Similarly, the double bond position you can put in this way. So that is another possibility. Double bond can also be exocyclic, that is outside the cycle. So this is another possibility. Now when it is 3 member ring, these are the possibilities, and when it is 4 member ring, we have drawn only one. And is it the only possibility? Actually here another type of structure is also possible. If you simply join these 2 carbon, here you will have 1 hydrogen, 1 hydrogen, 2 hydrogen, 2 hydrogen. So again it is matching with C4H6. So under 4 we are getting 2 structures possible, and under 3 we are getting 3 structures possible. So total number of structures will be basically 5. So step by step you have to think. First of all, it is cyclic. So as it is C4, so you can simply start with cyclobutane. But cyclobutane, if it is saturated, number of hydrogen will be high. So it has to be, there has to be some double bond. Then it is C4H6. Now once 4 member is done, you can move to 3 member, and under 3 member there are 3 possibilities. But under 4 member also this is one of the another possibility, though it is you can say 3 member as if connected together. That in that way also you can say it. And whatever, total number will be 5. Which of the following compounds has incorrect IUPAC nomenclature? Look at the first one. Here we have some ester group. And ester, how we do the nomenclature? Suppose if I write in general, this is the ester, then you have to write the name of this part, which is R prime. So in our case, R prime is ethyl. So you have to start with ethyl. Then rest of the part, you just have to count. This is the rest of the part. You have to count total number of carbon. Total number of carbon is 1, 2, 3, 4. So it must be but, but you have to end it with 8. Ethyl butanoate. So this is okay. It is not incorrect. Come to the molecule B. Here we have CHO. So numbering should be started from this point. 1, 2, 3, 4. So at 3 position you have methyl substituent, and in the longest chain you have 4 carbon. So 3-methyl butanol, it is absolutely correct. Come to the option C. Choose the longest chain 1, 2, 3, 4, 5. So numbering should, if I start from here 1, 2, 3, 4, 5. Then at 2 position you have methyl. Don't start the numbering from the left hand side. If you are doing this, then methyl will get 4 methyl, which is not correct. It should be minimum. So this is not correct. 1, 2, you have to start from left hand side because methyl is present at 2 position. So 2 methyl, longest chain 5 carbon, 3 pent, and it should be ending with one. 3 pentanone, the position of one is 3, so 3 pentanone. So all the first 3 are correct. That means D must be wrong. But what is the wrong? Here, this is the longest chain. Now in the longest chain, OH position that you have to write in such a way so that it is minimum. So that is why we will start the numbering from this position. If you are starting the numbering from left to right, OH will get number 3 position, which is not correct. Now here it is written as if we have done the numbering in the reverse order. If you do the numbering like this, then it is matching with the name given. But that is not correct, because this is the principal functional group and the green one is correct, not the blue one. So this is actually the wrong. So this will be our correct option, because we have to choose in which case there is incorrect IUPAC nomenclature present. Select the molecule in which all the atoms may lie on a single plane. That means sp3 carbon should not be present. Draw the first one, 4-nitrobenzaldehyde. Now benzene ring, it is planar, and when you have aldehyde group, now this carbon is also sp2 hybridized, and you have nitro, that will be also in the same plane. So this may be the correct option, but we will also draw the other 3. The second one is 4-methoxybenzaldehyde. This is also benzaldehyde, but now we have OMe. Now when you have OMe, so this CH3 is sp3 hybridized, and this part is basically tetrahedral. So it is not completely planar. That is, it is not correct. What about number 3? Now we have 4-methyl nitrobenzene. Now whenever you have written methyl, actually now you can see again you have sp3 hybridized carbon. So this part will not be planar. The last one, 4-nitro. And nitro group in extended way so that you can understand why it is planar. Acetophenol, COCH3. Now here also in this part you have sp3 carbon. C double bond is okay, it is sp2, but CH3 it is sp3, so it will not be planar. So considering all this, first option should be the correct option. Among Me3N, C5H5N, MECN, Me is methyl group, electronegativity of nitrogen, the order we have to find. Now Me3N, here 3 methyl groups attached with nitrogen. So this nitrogen, it is no, there is total 3 single bond, right? Now C5H5N, which is nothing but pyridine, this molecule. Now this nitrogen is sp2 hybridized. This is sp3 hybridized. And the last molecule, CH3C triple bond N. So in this case, it is sp. And now you got the answer. It is asking electronegativity order of nitrogen. So based on this hybridization of the nitrogen, because electronegativity that is directly related to S character, when S character is high, electronegativity will also be high. So maximum S character you will get here. After that, it is pyridine and then it is Me3N. So option A, MECN first, then pyridine, and then we have trimethylamine. So that is why this should be the correct option. And electronegativity same, that is not correct. So you have to draw the structure, then only you will be able to understand that it is the question you have to answer from the point of view of S character. Identify most acidic hydrogen in the given compound. Now look at the groups. Option C, B, A, D. So here A is this hydrogen. This is A. Then we have SH group. This hydrogen we are calling as C. Then we also have OH group, though this OH group is not marked. Here we have this OH, which is B. And here we have these 2 hydrogens are there. So any of this hydrogen you can consider as T. Now most acidic. So here if we look at the groups, we have COOH group. Then we have SH group. Then we have OH group. And then we have this CH2, and other side there is OH. So you just have to focus on this part. On one side CO group, which is electron withdrawal, other side we have COH. Now CO2H, as we call it, it is carboxylic acid. We also know that here H is attached to oxygen, H is attached to sulfur. They are also having some acidity. But if you simply compare alcohol and some carboxylic acid, obviously the carboxylic acid which will be most acidic, which is clear from the name itself. We call it carboxylic acid. Why? Because it is acidic, obviously, compared to the other groups. And also the reason you can understand, once you remove this H, you get, in general, if I write RCOO, there is a negative charge. Now, if you consider this resonance structure, you are getting another equivalent resonance structure. So these two are equivalent resonance structure. And whenever there is equivalent resonance structure generation, the stability because of resonance is very high. So these are the reasons why its acidity is high, because after H removal, the negative charge is very stable. But in this case, you will not get it. It is true that negative charge will be over oxygen, will be over sulfur. They are having some electronegativity, but this type of resonance is not present. And in this case, the negative charge will be generated over carbon. And after that, it can take part in resonance. But it is generated on carbon, not like the other three cases, where it is generated on heteroatom. So OH hydrogen, that is A, that should be having maximum acidity. And option 3 is the correct option. The number of chiral carbons present in the molecule given below. Now, chiral carbon means where force substituents that are attached to carbon that must be different, A, B, C, and D. If it is the case, then only it will be correct. Now, this part you can easily understand. All the 4 groups are different, isn't it? Now, look at this part. This is the carbon where 4 groups. Here we also have hydrogen. So, hydrogen is one group, another group, third group, fourth group. Now, the side carbon, that is this one, here also we have hydrogen. But these 4 sides, all are basically different, isn't it? Now look at the other part, that is in this nitrogen containing ring. This carbon is chiral, isn't it? Here also you have hydrogen, ethyl group, you have CH2CN, and this side all are different. This is also chiral, isn't it? This side, this side, this side, and you have a hydrogen. And if you look at the other part, this is CH2, this is CH2, this is CH3, they are not chiral. So these are the 5 places where you will get some chirality. This should be the answer. The dihedral angle in the staggered form of Newman projection of 1,1,1 trichloroethane. Now ethane is what? Ethane is C2H6, which you can write as CH3, and when you draw the Newman, it is easy to understand. This will be your CC bond. Suppose this is the front carbon, this is the rear carbon. So when you draw the Newman, it should be like this. That is the staggered form. If I write, it should be like this. But now it is 1,1,1 trichloro. So this is number 1 carbon, this is number 2 carbon. Now 1,1,1 trichloro. So all the 3 hydrogens, now it will be replaced by 3 chlorine atoms, and rest of the part is same. If you now draw the Newman, what you will get? You will get chlorine, chlorine, chlorine. This is the front carbon, back carbon with a circle, and here we will have 3 hydrogen just as before. Now it is asking dihedral angle in the staggered form in degree. So dihedral angle is basically this angle, which is 60 degree here. So answer will be 60 degree. Number of electrophilic centers in the given compound is. Electrophilic center means what? The center which itself is electron deficient and it is searching for some electron density. That means it is searching for some nucleophile. So we have to find those centers where nucleophilic attack is possible, right? Now here we have carbonyl group, and if I have any nucleophile, it can attack here and negative charge will be over oxygen. So this type of attack is possible. Next, we can also do the attack on this carbon, because if I do so, now this double bond will be shifted here and again negative charge will be over oxygen. So it is not direct attack to C double bond O, but we are attacking at alpha beta position. So this is alpha with respect to CO, this is beta position. So we call this type of system, I am talking about this type of system, alpha beta unsaturated carbonyl, because with respect to carbonyl group, this is alpha beta unsaturation. So for here, this is also another nucleophilic center. Now this part, if you draw elaborately, it will be like this. In this case also, if you treat it with nucleophile, then negative charge will be over nitrogen. So nucleophilic attack is possible. So these will be the three positions where nucleophilic attack will be possible. So answer should be 3. Total number of possible stereoisomers of dimethylcyclopentane. Dimethylcyclopentane. It is not mentioned the position, what is the position of methyl, but it is simply mentioned that 2 methyl groups will be there and it will be cyclopentane. So cyclopentane, it is okay, and 2 methyl groups should be there. And number of possible stereoisomers. So if it is not, there is stereoisomerism not possible, you should not count it when we will count the total number. Now the first possibility is if you place both the methyl groups in the same carbon. Now this carbon is obviously not chiral because two same groups are there. This side is same, this side is same. So this is should not be, we should not count it. Now the next possibility is if you place two methyl groups at one position, two position. Now when you are placing at 1 and 2 position, you can place it as both of them are Cs. You can also draw it, these two are actually equivalent. Whether you place it below the plane or above the plane, it doesn't matter, both are same. So it is Cs. So when you have Cs, there is a sigma plane, you can cut the molecule into same half. So this will not be optical, but if you consider the corresponding trans, so one will be above, another will be below. Now what will happen? You will not find any sigma plane, and in this case it will be chiral and it will have its another pair, or I can say it will have its enantiomeric pair. So when it is 1-2 substitution, under that you are getting Cs, you are getting trans, but Cs is not optically active, trans is optically active. So total number will be 3. Similar will be the case if you place the 2 methyl group at 1 and 3 position. Now when it is at 1 and 3 position, and under that when it is Cs, whether you draw it above the plane or below the plane doesn't matter, there will always be sigma plane, so it is not chiral. But if you consider its trans isomer, then enantiomeric pair is possible plus enantiomer, and that is why total will be 3. So 3 plus 3, our answer should be 6 because we have already cancelled it. Now if you are thinking why not the placing methyl to the next carbon, but if you position the methyl in the next carbon, again it will be another 1, 3. So only 2 types of possibilities are there, either actually 3 types of possibilities, 1, 1, 1, 2, 1, 3. But this we have cancelled. Under this we have 3, under this we have 3. So total it is 6. But 1, 4 is not possible because if you draw 1, it is actually again 1, 3, right? So answer will be 6. Sorry, so that is the end of this class. We have solved all the problems. Let me just check. So we will end the session here. Thank you for listening.